certain that there was going to be water there, so you know?
Yeah, okay, so maybe I can just put it here.
I love the bell.
Yeah. One conference we had at home. It's even better. Dun, dun, and then oh, what a sound! It is even better.
Okay. Just saying. Okay. One more minute. Good morning, everyone. We are about to start. Please take a seat. So welcome, everyone, to this invited lecture given by Professor Stefan Fenninger from Open to Transparent Energy System Modeling for the Next Quarter Century. Dr. Fenninger is an Associate Professor of Sustainable Energy Systems at the Faculty of Technology, Policy and Management at TU Delft. His research focuses on understanding technical, economic, and environmental trade-off between different possible ways to build 100% clean and renewable energy systems. Together with his team, he investigates three broad areas. One, understanding the variability of renewable energy spatial scales, ranging from individual buildings to the entire continent. Two, designing energy systems that can deal with and thrive on this variability. And three, exploring decision space of trade-off between sustainable energy and other issues. He created and currently leads the development of the open source energy system model tool Calliope, and he's also the creator and lead developer of the Renewables Ninja, a platform that allows users to simulate wind and solar power plants worldwide. Please join me in welcoming Professor Fenninger.
Good morning, and thanks for the kind introduction, Felipe. Many thanks also to the organizers for inviting me to speak. It's really a pleasure to be here and to interact with all of you. And as you can see, my title promises quite a lot, actually, so let's jump right in. And we actually have a few things to celebrate today. It's not just the 20th anniversary of this conference, but we also have some nice news from yesterday that you might have seen. First, in the first half of 2025, global renewable generation has overtaken global coal generation in electricity for the first time ever. So that's really great. Second, solar and wind growth together, so the growth in solar and wind electricity generation exceeded global demand growth, also for the first time ever. That's just from yesterday, and that really highlights the massive speed with which renewables are being deployed. And that's great news, of course. But at the same time, emissions overall are still growing. We all know that time is running out. We have targets. We'd like to stay within 1.5 or maybe 2 degrees Celsius globally. Achieving this is really difficult. So some parts of the transition are going faster than needed and also much faster than expected, but many parts are still slower. And I like this traffic light graphic from the German Institute for Economic Research. They update this every couple of months. This is for Germany only, and it shows us just the speed at which different parts or different technologies are being deployed relative to Germany's 2030 targets. So we can see here solar energy again. It's being deployed fast enough to make the 2030 target. Everything else is much slower than would be needed. So it's unlikely that these 2030 targets will be met in Germany. And of course, the picture is the same in many other parts of the world. Now, this is a problem for 2 reasons. Well, first of all, as we've seen or as we know, being fast in just one area, like deploying solar energy, doesn't by itself solve the climate issue. But there's another problem. Building, for example, lots of PV and ignoring other parts of the transition, other parts of the system cannot keep up. So there are problems there. For example, the grid. We have this issue in the Netherlands. Distribution grid investment did not keep up with the rapid growth in solar photovoltaics, and that's an issue now. We also heard this in yesterday's keynote. So this problem, the transition to renewables, it's accelerating, but it's often accelerating in a disjointed, unorganized way. It's managed project by project, not in an integrated fashion. Now, energy system models, in theory, should actually help us do this in a more coordinated way. So not just across the power system here, the green parts, but also the rest of the energy system, which also has to decarbonize industry, transport, aviation, heating, cooling, and the whole rest of the economy. That's the whole point of looking at the system as a whole and not just its parts. So looking forward to the future, what can we as energy system modelers do to better fulfill our potential to actually help this transition? Okay, so before we talk about the future, let's go back in time a little bit. 1984, that's the year the original Terminator movie came out. I don't know how many of you in the room have seen it, but you've probably heard of it. It's fear of AI, killer robots traveling back in time, that kind of thing. That was very on topic in the 1980s. It seems like in the 2020s, we're still afraid of AI for slightly different reasons. But there's also other interesting stuff that was happening back in the 80s and that are still relevant for us today. This book here, Groping in the Dark, the first decade of global modeling, was published in 1982. It's actually the conference proceedings of the 6th IASA Symposium on Global Modeling that happened all the way back in 1978, so almost 50 years ago. You can find this online. It's freely available, and it's a really interesting read. One thing that we can find in there is that in these proceedings, we have a record of the areas on which the attendees disagreed and the areas where they agreed. So there's 11 areas of disagreement. I just picked out 2 here. You can find the others if you look at the report online. Should models be normative or descriptive? Should models be big or small? I think those are questions that we could still argue about today, 50 years later. But what's even more interesting are the areas of agreement. There are, again, 13 areas of agreement in here, and I've picked 4 of them that I find particularly interesting. Number 5, the most important forces shaping the future are social and political, and these forces are the least well represented in the models so far. Now consider we're in the 70s, 50 years later, we're still struggling with this. Then 10, 11, 12, this is mostly about transparency, openness. Number 10, Non-technical audience should be able to understand the model's assumptions. Number 11, modelers should share their data as much as possible. Consider that at this point in time, concepts such as free software, open source software, open data didn't even exist yet. So the language is different, but the ideas are here. And then number 12, model users should be involved in the modeling process as directly and frequently as possible. Now, I find it really interesting that we have all of this written down back in '82. And I want to talk especially about these two things, so social factors and transparency today. And why have we been discussing these for such a very long time? So if we fast forward to 2014, I thought it was a good idea to also write down challenges for energy system modeling. And these are the 4 areas that I came up with back then. And I think that on the first 2 in particular, we actually did a pretty good job. And that's really good, because to have any hope of meeting at least some of our global climate targets, we need a lot of local action. Small, local efforts that together add up to a global shift. And having high-resolution models that can tackle the system's technical complexity, that can really help to inform those actions. But the second set of challenges, the ones in purple down here, they're maybe even more important for models to really be relevant and remain relevant and become more relevant for informing this local implementation action. So I'm going to simplify this down a little bit to just transparency and social factors. I'm leaving aside uncertainty, otherwise there's simply too many things to talk about in the time that we have. And to be honest, I'm also not really sure anymore why I originally lumped transparency and uncertainty together into one box. This was my first PhD paper, so I hope I can be forgiven for this. But today, let's look at these 2. And maybe even look into ways that would potentially allow us to deal with both of them simultaneously. Okay, so introduction is out of the way. Let's very briefly talk about the progress in resolution and complexity, and then really go into these gaps, transparency and social factors, and what to actually do about them before jumping to some conclusions. So, resolution and complexity. And I think I'm just going to say that, well, I've said it already, and I'll repeat it again, that we've really made great progress on these. Spatial resolution, temporal resolution, sector coupling, this technical complexity of having sector-coupled models. And when I was preparing for this, I thought, well, I'm going to show some examples and the evolution of all this through time. But to be honest, if I do that, I will run out of time simply doing that. There are so many examples to list, including examples from many of the people in the room here. If we just look at the conference program, we see work that's been presented already or presentations that are yet to come that really highlight this point, that we're really doing a very good job on this. I still want to just show one example, of course, to really highlight how models are not just high resolution in space, high resolution in time, tackling this energy sector complexity, but moving also beyond complexity in just the energy system itself, to look at connections between energy and environment, energy and water, exactly the kinds of things that we care about at this conference. So in this example here, this is work led by Paula Borba, who was a visiting PhD in my group. She's now working at the Brazilian Institute for Space Research, and she built a high-resolution energy system model of Brazil, and then she coupled this with a detailed land use analysis to show that land conservation and a fully renewable Brazil are actually compatible, and they're even synergistic by shifting land away from biofuels and allowing reforestation of conservation-relevant lands. And I just want to say that routinely having this kind of rich detail in models, it's really an achievement that we've made as a field over the past decade or so. So I think it's really something that we can collaboratively pat our own backs for having achieved. And of course we could say, okay, we've made progress, there's still a lot to do, also on these topics of resolution and complexity, but we can leave that as a story for another time and move on to transparency and social factors, so these gaps. And let's start with transparency. And transparency, that really leads us to talk about openness, about open models, open data, open code. Now, why should models be open? I'm not saying that there are only 4 reasons for this, but these are the 4 reasons that we came up with back in 2017 to push the community towards more openness. And I have to say also here, the progress has really been massive. We now have a flourishing of open models, of open code, open data. These things are now the standard. If I think about the reasons here, the reasons, I've classified them now, not back then, but I've added this now. 2 reasons in blue, internal to research. 2 reasons more external to research. So this collaboration across the science policy boundary, the fact that these models are relevant to societal debates. I think those are the ones that are particularly important in the next 25 years. And all of this, when you come to really think about it, it's really not about openness per se, but about transparency and understandability. It's about understanding what's really inside a model. So this is a lot more than putting some code or some data up on GitHub or another open repository. So you could say, okay, this whole transparency thing, isn't this a solved problem? And we've seen that complexity and resolution of these models is increasing, has increased and is still increasing. Openness of code and data has increased, is still increasing. But to some extent, don't these 2 trends maybe also almost cancel each other out? This transparency and understandability, have we really achieved it? And this is from a paper, Scheller et al., where they find that PhD candidates rate model usability as lower than senior researchers, and they found that often these PhD candidates invest very large amounts of effort to get a full picture of the model. Now, if even a PhD candidate finds it hard, where the supervisor is probably sitting next to them, the supervisor that probably built the model to begin with, how then are people even further away from this modeling activity supposed to really make sense of it and do that, within a period of the attention span and the resources they have to actually do that? So perhaps this is not a solved problem quite yet. Let's look at social factors. I haven't really defined this very well. What are these social factors? And partially I've done that on purpose. But I find it also interesting here to also go back and look at what the community has been saying about this. Again, we can look at the same report from '82, and one of the symposium participants is quoted here: "The final task is to represent the behavior of social groups within a model." And we can fast forward again to 40 years later. Diana Susser and her colleagues concluded that users want better models recording the representation of environmental and social factors. And there are many other examples in these 40 decades where this call has been made for integrating social factors into these energy system models. And we can ask ourselves, why have these calls persisted over these decades? Is it that no progress has been made, or progress has been made but only slowly, not quickly enough? Or is it maybe that integrating these social factors into models such as mathematical optimization models are just that's just difficult task, or that that paradigm doesn't really suit the integration of social factors? There may be many other reasons as well, and I think this is also something where we could have a long discussion on. So let's just park it and actually look again at an example of how we can integrate a social factor into an energy system model, into a mathematical optimization model. So this is an example from Mei-Jin Chen, a PhD candidate in my group. And I'm going to walk you through this. Here we are using our sector-coupled high-resolution European energy system model. You can see below here on the x-axis which countries are included. And each gray dot on the vertical spread here represents a single near-optimal solution, a possible future European energy system that's fully renewable without any fuel imports. So those are some assumptions that go in there. And we have different possible solutions. So these different gray dots, one of them might represent a system with a lot of photovoltaic generation, another one might represent a system with a lot of wind, yet another one a system where we rely more on electrification than on synthetic fuels, things like that. And we are now looking at how each of these solutions performs across all these countries in terms of one specific metric: how much additional household investment burden it requires compared to historical household expenditures on appliances in these countries to make the heating transition happen. So this metric is normalized by country, and we have this red line here, the historical household expenditure baseline. And then we can highlight one of these possible future European systems. The one here in purple, that's an example where we see that some countries are asked or forced in this model world to invest a lot more into household heating than their historical baseline. And it's also very unevenly distributed. And then we have another solution, the one in green here, where all the countries are actually below their historical baseline, and the distribution is also much more even. Now, of course, the optimization here is for total European cost. So it doesn't consider details such as household investment burden. And if we were not to explicitly look into this, we wouldn't even notice that this is potentially a problem. So Mei-Jin is calling the original model a disparity unaware model, and she then adds constraints to the model. For example, a constraint that prevents any one country from having a higher investment burden than its historical baseline. And that works. It pushes all of these solutions down to below the red line, and it pushes total system cost up by a few percent. So it's perfectly feasible. But this is still just a crutch. We are adding more economic constraints to a cost minimizing model. So it's a very reductionistic way of depicting these social factors. And ultimately, we are left to wonder whether mathematical optimization is really the right tool, perhaps, to actually look at this kind of problem. And again, that's an interesting topic that we could talk a lot more about, but let's park that thought and move on. So this is the summary so far. We talked about transparency and social factors. Transparency, more open source, more open data. Complexity and higher resolution also going up, and we're left with the thought that transparency and understandability are still a challenge. And on these social factors, we've seen that there's been calls to include them in models for decades. And there are some solutions. We can apply some band-aids, but it feels a bit unsatisfactory. So, what should we do? And as a reminder, I also said, can we maybe make progress on both of these in some way at the same time? This book I really highly recommend, Escape from Model Land by Erica Thompson. And Erica looks at how mathematical models are built, models on a range of topics, the spread of COVID-19, global climate models, and many others more. And one of her arguments in this book is that when you make a model of a socio-technical system, such as decarbonization of the energy system, then you create a model land, and that model land is not an objective representation of reality. It takes on the social context, the assumptions, the biases, and so on of the person making the model. Now, you might say, whoa, wait a moment, that's a problem. The biases of the creator, they should not enter into the model because the model should be purely objective. Or you could say, hey, that's actually a feature. It's not a bug. Because we can see that, okay, society is already entering into these models indirectly via the role of the person making the model, via the processes that lead to this model being made. And if we think that society is making its way into these models, for example, via the worldviews of the modelers building the models, then it actually becomes relevant to better understand, well, what do these modelers actually think? What's actually going on inside our heads? What do we believe? What do they believe? Well, I should say we, because I'm one of them, right? And that's what Franziska Bock, the PhD candidate in my group, is doing. Here, we showed 166 modelers a series of statements, asking whether they agree or disagree with them. Now, you don't have to worry about reading the text here. I don't believe you can. The point is that we have 18 statements, and we see a very clear pattern. You can go look at the paper online or in the slides later if you want to read these statements in more detail. So we have some large areas of consensus here. At the bottom, where the bars are mostly green, those are statements that most of the respondents agree with. At the top, where the bar is mostly purple, that's statements where most of the respondents disagree with the statement. So there's consensus. For example, statement number 18. Even recognized modelers are biased so that their analyses and recommendations should be scrutinized. Most agreed on that. I think that's a sensible statement. The interesting part is in the middle, where we actually see polarization. So there are some statements where about half of the respondents agree and about half of the respondents disagree with the statement. For example, statement number 6. In their work, modelers can ultimately get to the objective truth. Now, I think we have a little bit of time to do a little experiment and see what you in this room think about that. So let's see how that goes. So we have the statement, in their work, modelers can ultimately get to the objective truth. Now, if you agree with that statement, please raise your hand. And don't be shy, I'm not going to pick on anyone. So let's see if that works. Raise your hand if you agree with the statement here, in their work, modelers can ultimately get to the objective truth. Yes, excellent. Response rate is pretty good. It's not going to be a very quantitative study because I'm just eyeballing the room and estimating how many hands I see. Okay, so the statement, in their work, modelers can ultimately get to the objective truth. If you disagree with the statement, so you think modelers cannot get to the objective truth, please raise your hand now. Okay, interesting. I think that this shows us how interesting a topic this is and how much additional work we need to do. I think the group in here is actually leaning more, quite visibly more towards disagreeing with the statement. Now, I'm not saying, I mean, there's no right answer here, right? But it's interesting to see, actually, how different communities, how different groups of people see these issues. And it's also something we go into a little bit in this paper. So thanks for that. And like I said, I think this is it's a really interesting area to look more into. Franziska came up with these two groups, the positivist modelers that think models can or should be objective, and the post-positivist modelers that do not think objective truth in these models is achievable. And again, as before, when we looked back at the 70s and 80s, what I think is particularly interesting is not just where people disagree, but also where they agree. So I'm a practical person, and I like to think about how to solve problems in a practical way. And one area of agreement here is that model-based scenarios cannot be interpreted responsibly without knowledge of the model assumptions and data. So this really highlights how actually these two things we're talking about are closely connected together. So these social factors, the assumptions inside the model, and the fact that we need transparency to actually understand these assumptions. So we're starting to approach maybe some understanding of how these two are actually connected. Okay, so let's also talk a little bit more about this transparency. So I showed you this example earlier, the study on Brazil, and that's a model result, right? This map here is a result coming out of a model. And we can look at this model, and then we can try to peer inside the model, and we can see that, well, okay, this model is made up of some data, it's made up of code, maybe a little bit of text, some explanation, some documentation, and so on. But in a study like this, it's probably a rather large and complicated model that might be quite difficult to understand. So perhaps a model that might be openly available, but not necessarily very transparent. So could we perhaps break this model down into smaller pieces that become in themselves more understandable again? Well, let's try to do that. So we can break it up into individual building blocks. And it turns out that a lot of what is happening here is actually simply data processing, generating renewable electricity supply profiles, gathering and processing assumptions on technology costs, processing statistical data to model industrial, feedstock demands or other energy demands, and so on and so forth. And when you look at it this way, the system model part comes at a very long chain of these other components, these other building blocks that add up layers and layers of assumptions, data processing, that in the end is then fed into the system model, whether that's an optimization model, a simulation model, a system dynamics model, what name you. Now, some of these boxes might be a little bit more fundamental than other ones. They might include assumptions that then permeate throughout the whole model. And if we're looking at one example, land availability, land use, if we're talking about models that look at the spatial deployment of renewables, this might be a very important assumption. How much of a specific technology, how much of specific infrastructure can you actually put in specific places? So this box might be quite fundamental to the model. And if I can break up my model into pieces like this, then I can focus my attention on one specific area at a time. I can give this building block to, let's say, an expert in land use assessment to maybe play around with, to give me feedback, or even to actively work on and contribute to. Or even more importantly, I can maybe show this to a non-expert. I can show what's going on here, or get even a non-expert to play around with this and give me some feedback on whether what I'm doing makes sense or not. So this is basically reductionism, where we're breaking down the problem into smaller parts to allow us to tackle it. And we are working on a system to do this right now, so I can actually show you an example of how this looks. So if we're sticking to this land use example, we're taking in a series of geospatial input data in a fully automated manner. Then we have some human-readable configuration that defines how these land use decisions are actually made. Then we have some code that processes all of this and gives us results, the areas that are suitable for specific technologies to be built in. And we package all of this up into a standardized building block. And this building block is then connected to other building blocks. So, for example, the region shapes, here it's the country of Mexico, together with its offshore exclusive economic zones. Those come from another module that actually makes these geospatial boundaries. And then we pass on the results to subsequent building blocks for further processing. So like I said, this is something we're working on right now. We started to actually build this approach, and I've showed you the module highlighted in green here, the area potentials module. I showed you how it takes inputs from what we call the geoboundaries module. The resolution of that module is fully flexible, so it's configurable. You can say, I want Mexico, or I want Europe with all the countries and all the sub-country units inside those countries. That should be my unit of analysis. That's fully configurable. And then those, the next in the chain here is the capacity factors module, which then takes the available areas and generates capacity factors for the renewable technologies that we place there, and so on and so forth. And at the end of this chain, we end up with what we call the model integration module, which actually takes all of these data together and builds an energy system model. We call the whole thing Clio at the moment because it was designed as a companion for our Calliope open source energy system modeling software. But the key point is that by customizing this final step, this integration module, it's fully model agnostic. You can use this with any other tool, whether it's PIPESA or Energy Plan or what name you. And that's the idea behind this. And the technical implementation of this approach is actually the brainchild of Ivan Ruiz Manuel, another PhD candidate in my group, and him and Jan Launer, another PhD, together are actually leading the implementation of this. So I have to highlight, this is still work in progress. We're actually working on it actively as I speak. It is open source, it's available online, but I'm not pointing you to it because the documentation is a bit shaky right now, but you can find it if you search for it. But do get in touch if you're interested in this. We are using it internally already to build European system models, and we're starting to work with partners to actually contribute and work on additional modules in this ecosystem. So our aim here is to also run globally, not just in Europe, but maybe a little bit different from other efforts to build these kind of global databases or modeling systems. Our main effort is really to build an ecosystem here of modules, maintainable, transparent, understandable modules that can be mixed and matched thanks to this implementation of a standard interface and all the technical details that I'm not going to bore you with here, but happy to talk about later if you wish. And what I really want to highlight here is the ability to then reuse different modules in different contexts. So the land use example, again, if maybe all you need is land use analysis and one or two other things, and that's really where you focus your attention, then you can take this module and you can build on it, you can improve it, you can add additional detail to it. That will be useful for you, but it'll also be useful for everyone else who is using this module in their own processing pipeline. And then adding up all these pieces together, you will still end up with a highly complex state-of-the-art system model, but it will be more understandable what's going on inside. And that, I think, is really also integrating these social factors directly into making the model itself. And I think this is also a topic that's interesting for the SDEWES community. And the thinking behind this is ultimately also a bit of an evolution of lessons learned from building and running Renewables Ninja, which I think has been a huge success. And the lesson is really, if you do one thing well, and you do that in an understandable and accessible way, then it becomes a valuable resource. So in a sense, what we'd like to do now is to build almost like a meta Renewables Ninja, where we have these individual building blocks that do one thing well, but add up to something that's greater than the sum of its parts. And of course, to look into doing this collaboratively with different people across institutions and different areas of expertise. Okay, so I realize that I am now, at this moment in time, the only obstacle between, well, you and beautiful sunshine outside, lunch, and then the social events of this afternoon. So I'm going to try to keep it short, recap my main messages. We can then jump into questions and move on to lunch. I'm very happy to talk about this stuff also later today or in the coming days. I'll be here until Friday. So I promise to somehow tackle both transparency and social factors at the same time, and I'll leave it to you to judge whether or not I have, to some extent, succeeded in that. But here's my conclusion in the form of, I have to apologize, a very badly drawn comic. So putting people into models can work, but we should also consider bringing models to the people in digestible pieces and better understanding what goes on inside the heads of model builders and ideally also the model users. And I believe that doing this will help us really advance the state of the art in energy system modeling, and will address both transparency and these social factors at the same time. And that's my main conclusion in non-cartoon form. I'd love to talk to you, especially if you're interested in working on and collaborating on these emerging areas of work. So thanks a lot for listening. I'm looking forward to the discussion.
Thank you very much for this very interesting presentation. I will go ahead with the first question, maybe two, and then I will open the mic for everyone who wants to ask. So basically, looking at your presentation, I've been thinking that there are many models or type of models that I use. We develop energy system models that are fairly detailed in terms of resolution, time resolution. And then we also use other models that are maybe more spatial resolutions, such as integrated assessment model, also linking energy, water, land systems, and so on. So you have this basically very wide spectrum of models. But then we are basically all aware that of this famous quote that basically says, all models are wrong, but some of them are useful. So I'm thinking, based on your experience, what makes a model useful? If you see, this whole variety of basically different models.
Thanks. That's a very good question, and also one I think that we could spend easily the next few hours debating. I think it comes down to the purpose of the model, right? And so we have this wide range of models, and these models have different purposes. Some of them are very detailed models, trying to do one thing right. For example, I don't know, forecast wind generation. There we can actually we can assess how well that model does by comparing the forecast to the actual realization. When we start talking about models that are used in decision making, or models that look at the system as a whole, look far into the future, integrate social, economic criteria that are difficult to actually validate or impossible to validate, then I think we can look to the idea of post-normal science, which basically says that if we're in this area where the decision stakes are very high and the uncertainty is very high, then what starts to matter very much is the process. So you could say in a way almost sometimes, it's like sometimes it's better to be transparent than to be right, because it's difficult to even say what right is, or there is no right answer. But if the model is transparent, it can be used, it can be investigated, it can be examined by the people that might make decisions based on that model. And the process can become more inclusive. You can bring, as we've seen already as one of the areas of agreement back in '78, the users of the model into the process of developing the model. So that's, I think that's an area to go into.
Thank you. I have one more question, or if I have time, then I will go with a third question. You brought up Terminator, and you said, we were basically back then afraid of AI. But I'm thinking, how do you see actually, deep learning models, machine learning models, in general, artificial intelligence, helping maybe developing these models? Is this technology going to be useful? Can we maybe, rely to create some synthetic data for the data processing that you were showing before. How do you actually see these new type of technologies in helping us developing these energy system models?
Yeah, thanks. Also, very good question. Again, I think there are opportunities and dangers. There are many opportunities, clearly, opportunities that are already being exploited. You can generate synthetic data, as you pointed out. You can use AI to avoid having to run a very large optimization model over and over again. For example, if you train on model outputs, stuff like that, that can be useful. I think the danger is when you start using, building an over-reliance on AI methods, which lead to actually deepening of the sort of black boxification of models. So there's a danger that you go in the opposite direction of opening up and making the model more transparent by relying on methods that are in themselves mostly black boxes. So yeah, opportunity and danger.
Yeah, and maybe one small short question, and then I'll pass the mic. I was very curious about the work about introducing social constraints. Something that we have also been thinking about. So when you run the models, you see these constraints and you see their shadow prices. So what kind of interpretation you can actually make out of this marginal cost of social impacts, or what kind of ideas you can actually get from these shadow prices?
Yeah, I mean, marginal cost of social impact for sure. I have to say we haven't actually looked at the shadow prices in that model, but that's definitely an interesting area to explore more. And I think it's also something that is increasingly being realized by the modeling community, or at least the community using these large-scale optimization models, that there's a lot of interesting information kind of locked away in these shadow prices. So I agree that's an interesting topic to look into more.
Thank you. Neven? And then we go with Benedetto.
Economics is called dismal science because it's trying to use statistics in order to see what people think, decide to do, but it's actually trying to cover an agent-based situation where many people behave in different ways. In a way, it resembles thermodynamics, but economic models actually provide us a quite good picture of reality, even though people behave in most unexpected ways sometimes. So why this wide untrust of models if they actually do quite good insight?
Good question. So I think it's good to differentiate maybe a bit more explicitly what kind of models I'm mostly talking about here. So we typically call them techno-economic models, right? I think the economists in the room will laugh at this because it's not economics at all. The economics mostly comes in the form of cost optimization, which the model does. So the assumption that we like to have the cost minimal system. So let's talk about that aspect first. And I think there's been a lot of work recently which has shown us that actually, well, the real world is not, it actually does not work like that. Real world planning decisions are not made on the basis of cost optimization or cost minimization. So this flourishing of MGA methods, modeling to generate alternatives, looking for near optimal solutions rather than just optimal solutions is kind of one, I think, response to that. But we're also seeing that that's actually still, in a way, a crutch. It's trying to hack, it's trying to apply a hack to these methods. So there's a preprint, I think, maybe a week ago or so from Evelina Trutnevita's group at the University of Geneva. I'm pretty sure at least one one of Evelina's group members is in the room, and I could probably provide more background on that, but they've done backcasting exercise to look at how big is actually the difference between the cost optimal transition and the real transition costs in different European countries, and found that the costs, depending on which country you look at, is something like 50% to several 100% higher than the cost optimal one. So that really throws a lot of doubt on using this techno-economic cost minimizing model as a way to guide the renewable or the energy transition.
Thank you. Next, Benedetto.
Benedetto Anastasi from Tor Vergata University of Rome. So thanks, Stefan, for the presentation. My question is about understandability. Generally, there is maybe the issue that between transparency and understandability, we are still within the energy modelers community. Okay, I use PIPSA, I'm not using energy plan, okay, how to understand, how can be replicable my model. My question is, then the results of the model, they go to plan for energy transition of a country, and we try to push the citizen engagement. Please do comments, then we will respond. How do you see this process of understandability for citizens of the results of the model? Because sometimes you say, okay, the Times model, for instance, in my case in Italy, is saying that in 2050 nuclear is still an option, or another model say no, completely the vice versa, and then the citizen is completely lost.
Yeah.
Thank you.
Yeah, so that's a really interesting question to think about. And I mean, it goes exactly in the same direction as what we were just talking about, right? It's times it's cost minimizing or maybe social welfare maximizing. But it's very stupid in the sense that if you say, if your assumption is, well, the cost of nuclear is relatively to say solar PV is low, then the model is going to build nuclear, and it's going to say that's the answer, right? Now the problem arises when someone looks at this and isn't exactly sure what the process was of arriving at the end result, and sees it as maybe a prediction or as the optimal situation which Italy should find itself in. And I think this brings us back to this point of understanding better what's actually going on inside people's minds, not just when they make the models, but also when they look at the model results. So and I think it's an open question at the moment. There's been some work on this, for example, for IPCC reports. How do people actually understand the graphics, the figures in IPCC reports? Do people actually understand the way that uncertainty is supposed to be communicated in these plots, yes or no? And I think the answer is perhaps, but we don't really know. Like, do the users of this Italian Times study, do they understand that cost minimization went into it, that the assumptions for nuclear power were X and Y, or do they not? Is this idea, for example, of cost minimization, has that come across to the users, and how do the users see that as opposed to the modelers? I think that's an area where we need to do more work to better understand.
Thank you. So the gentleman there, and we might have time for one or two more questions. Then Isaac, and then Shir.
Good morning. Thank you so much for the presentation. And Stefano Mazzoni from the University of Roma Tor Vergata as well. I'm working on energy system modeling since almost 1 decade as well. And there is one very interesting question that I have to ask you. I agree with you to bring the model to the people, but from a modeling perspective, let's say that there is an input, an output, and attributes that characterize the models. How you believe that the attributes can be specified to different customers, different business model on a country level, because I think that this is something very difficult to calibrate on the same kind of model if you apply to a country to another one, or to a stakeholders, or to a TSO. So how you think that the attributes can be customized, because the transfer function is the same, let's say DNI input, electrical power output, but then there is a big word inside the model that can be differently specified how to use it.
Okay, so I think if I understand your question correctly, it's about customizing a model to a specific context, and maybe the assumptions inside the model to a specific context, and doing that in a way that allows you to cover these different contexts within one, let's say, framework or model setup.
The point is that if you need to bring it to people, the model should not differ too much between input and output, but the specification of the attributes that each user can input in the model can change.
Processes to support simulation and many, many others along those lines, and wider even. I would like to ask, regarding your second recommendation for smaller, more what would you think about such opportunities to support pathways to increase energy access, increase basic services, and sustainable development in general?
Yeah, I think that those are perfectly suited to actually this approach. So allowing new types of assumptions, new types of focus areas for such a modeling system to enter by just adding a new module. I think that's one of the reasons actually expanding this modeling world to look at new topics to build such a modular approach.
All right. Thank you so much, everyone, for being here. With this, we conclude this invited lecture. Thank you, Professor Fenninger, for very interesting presentation. So we go for lunch, and then we have the social event and dinner this afternoon. So see you all. Thank you for coming. Very nice presentation.
Thank you. Thanks.
And interesting.